So power rule for a couple of these, and the sum or difference rule. Second derivative, 12x minus 8. Here, let me. So then let's do third derivative is going to be 12. And then fourth derivative, f fourth of x is 0. This is why I said we're going to find them all. After, well, really after 3, 4 and on are just 0. So I'm just going to put all derivatives after the fourth, after really the third, I guess, are 0. So we did find them all. Alright, so this will, with polynomials, this will always happen. It'll always, the more derivatives you do, you'll eventually get to 0. Any other function, square root of x, 1 over x, quotient, it will, e to the x sign, it will not work. It will not be the same. Okay, so that's, that, again, f prime, f double prime, f triple, and then we start to use the parentheses, same with the y's. Let's do another one. Here we're going to do the first 5 derivatives, because this one will go on forever if we get them all. It just keeps going. I like this one though because there's a pattern. Okay, now we're going to do 1 over z with respect to the z variable. Do you agree we could do quotient rule? Right? It's a fraction. You can always do quotient rule here. It's going to be easier in this one though if I change this to z to the negative 1 power. By the way, it's really 1, but I just moved this z up, and I made it a negative exponent in the numerator. It's going to be easier to do them all a lot faster. Quotient rule would work on all of these, but this is going to be a little faster. So first derivative, f prime of z, power rule, negative 1, z, now subtract 1, so negative 2. I'm going to change that here because final answer is no negative exponents. So I keep the negative 1, and I just move this to the denominator. So z squared is now on the bottom. So that's the first derivative. Now I'm going to keep going with the second derivative. If I'm going to go back to an easier form, I'm going to use this one, because then I can just do power rule. So power rule, I bring the negative 2 down. It's negative 1 times negative 2, positive 2. Z, subtract 1 is negative 3. And then just change this so it's still the 2 there. And I put the z cubed back on bottom. So I can continue to use these, but the final answer I changed to positive. A couple more, triple prime. Negative power rule, negative 3 times 2 is negative 6. Z, going to subtract 1, negative 4. So this will be a negative 6 over z to the 4th. And by now, you can kind of just see the pattern too. You didn't actually want to do the next one. You guys see how it's alternating signs. Anytime. Do you see what happened in the denominator to the exponent? 2, 3, 4, just going up 1. So I know this one's going to go, it's going to be z to the 5th. And to get, it was 1 here, 2, negative 6. They're just taking the previous number and multiplying. Negative 3 times 2 is negative 6. So just showing you there's patterns. Negative 4 times negative 6 is 24. Z to the negative 5. And so I'll rewrite that so it only has positive exponents, so 24 over z to the 5th. Final one, the 5th derivative. Power rule again, I bring the negative 5 down, so 24 times negative 5 is negative 20. Z to the negative 6. Z to negative 6. So then I change this to a z to the 6th. Okay, there we go. So there's the 5 derivatives. And that's all I want to do before we look. That's higher order derivatives. Now I want to look at some applications. So, is there an answer about derivative of a derivative? We normally go to second derivative is pretty common, first and second. At times a third, at times, but usually we don't go much further than 2, maybe 3. Ready to move on? Again, important point. Polynomials. I could ask you, what's the 90th derivative? It always goes to 0. All right. So at the bottom of the page, we're going to start. I explained. We're going to start to look on the next couple pages about some applications. Applications of rates of change. This is like actually calculus at its core. Like calculus is half the class is basically rates of change. Pretty much one of the main topics. So rates of change, and how can we apply this? There's lots of different settings that we can do right now. There's more later on, but here's some that we can do now. We're going to do some with changing shapes. Shapes are changing, so the rate of change of shapes. Parabolic motion. You guys might have done that in the past, or did anybody in physics or did physics talk about parabolic, like a parabola? There's some business applications. Falling body is kind of the same thing as this. It's like you drop something, and you can study the rates of change of that object, that body. And finally, if you did physics, you definitely talk about this: position, velocity, acceleration, and how they relate. So that's a good one. Okay, one last thing before we do this, guys. This is just standard moving forward. I might help you out, say instantaneous, but if I just say rate of change, it's assumed to be the IREC, not the AREC. So if I want average velocity or average rate of change, I'll say the word average. If I just say rate of change, it means derivative, instantaneous. Okay, so that intros it. Mainly what I'm going to do in the next couple pages is just give you several examples of these different types. So the first one, and I kind of went in order of the ones I described there. First one is simply you have a shape. It could be a triangle, circle, prism, any type of geometric shape, basically. It's going to ask you to find the rate of change of that shape in respect to the radius. So basically the shape is, maybe it's a triangle changing size, and when the radius, when the base or when the height is a certain value, how fast is that triangle changing? So what's the rate of change of the area, or what's the rate of change of the perimeter or the circumference? So it can ask you about different things. It all starts with the geometry formula. So let's look at the first one here. Volume, so rate of change of the volume of a sphere with respect to its radius. Volume in respect to r. Anybody remember the volume formula for a sphere? Let's say start, you've got to know the formula for a shape. No? 4/3 pi r cubed. Back in geometry. Okay, now that's just the volume formula for a sphere. The question is what's the rate of change? That's derivative. So f prime of r is what they want. Okay, now here's something, guys. This is just a number. Right? All of that is a number. So don't think you have to do product rule or anything here. 4/3 is a number. Pi is a number. Those are all just values in front of your r cubed. So you treat it as if it was just like the 2r cubed, right? You just bring down the 3, and it's like that, right? 6r squared. Same thing here. I'm just going to bring down the 3 here. Evaluate that. So it'll be 12/3, which is 4. Or you can cancel these and be 4 pi. You keep the r, you subtract the 1 from 3, and you get 2. So only thing that might be tricky there is just saying, all right, the 3, well, that's all a number. Pi just stays out front, right? This is the constant multiple rule. You can do the derivative of r cubed, well, numbers just stay out front, and that's it. Let's see, evaluate the rate of change. So v prime, we already have it, at a radius of 5 and 10. So all I want is to plug in 5 and then plug in 10. This is setting something up. Often if the problem starts with pi in it, you can leave your answer in terms of pi. So like here, I'm gonna leave my answers in terms of pi. 5 squared order of operations is first. It's 25 times 4, so I got 100 pi. And it didn't give us any units, so it's 100 pi. You can put units in the It'll be units per unit squared because we don't actually have the amount of 2 units. 10 squared is 100 times 4, 400 pi. So what you can see, it actually, so we, from 5 to 10, we actually doubled the radius, but the volume, the rate of change of the volume was multiplied by 4. Okay, I'm going to actually skip C, because I want to make sure, I went a little long earlier, so I want to make sure I get to the next couple. Done for that one? Start with the formula and go from there. Let's do one more. Now this one, rate of change of the area of an equilateral triangle with respect to a side length S. Okay, now area of a triangle, you guys probably know that one. Anybody? No. No, you know this one. Area of a triangle. The what? Oh, yeah. I'm not giving this one to you. You guys know this one. Come on. Area of a triangle. There's no way you could be in calculus without knowing the area formula for a triangle. Thank you, Rachel. Half base times height. I don't know what you said. Something with width. I didn't quite hear.
The bottom part times the top part divided by half.
You times that.
Did I say times that?
I don't
care.
I don't know. Half base times height. Thank you for saving us. So what they want though is this. There's actually a formula for an equilateral triangle that's more specific than this. This is based on base and height. Equilateral triangle, you can get it based only on a side length S. So what we need to do is actually develop this formula a little bit. Starts with this. These are all S. So you might want to, this one's going to take a little bit of room, so maybe off to the side or somewhere on the right. You might want to just write in what I'm doing with this diagram, how to get this. Because sometimes it might, here's the formula directly. Other times you might have to just do a step or two to develop the formula. What they want is to get this formula so there's no longer B and H, but only S's in it. Only in terms of the variable S. Would you agree that the base is S here? Okay, that's on because it's the bottom, so this is S. The height is not S. The height is right here. That's the height. That's what I gotta find is this line. Equilateral triangle. Since the angles are all equal in an equilateral, an equiangular triangle, what's the measure?
60.
They're all 60, right? Since a triangle has a sum of 180 for the angles. Now this one up here, I split it. So it's 30 and 30. And the height went straight down at a 90-degree angle. The way we're going to do this is 30, 60, 90, the pattern from geometry. And you probably did it in pre-calc when you were developing the unit circle. You probably started by doing 30, 60, 90 triangles to get the pattern. You did. Pi over to get all the. We started with pi over 6.
This was very
Okay, well, eventually, but I'm guessing you started with 3069 to develop. So here's the pattern: x, 2x, and x radical 3. Look familiar from geometry? That might have been a while, but this is the pattern. All right, so basically this. This is s. This one down here is going to be half of this hypotenuse length. So right here, this one right here is going to be half of s. And that makes sense. We kind of cut this in half anyways. This is all s. This right here is half s. So this length down here is 1/2 s. From here to here. Then the height that we want right here is whatever this is times radical 3. 1/2 times radical 3. Oh, s. I'm sorry. 1/2 s radical 3. I'm going to fill it in down here again. 1/2. So the height, 1/2 s radical 3. All right, we simplify that a little bit, and that's the formula. Okay. Again, start with the formula, develop it. I didn't expect you on this one to remember this. This is why I did this one here in class. But you might have developed the formula a little bit. This one was based on 30, 60, 90. So I simplify this. Now, the variables, it's s and s. These are all multiplied, so that's going to be s squared. Then I've got, in the numerator, I've got a radical 3, and then 1/2 times 1/2 is 1/4. And what I can do is, this is in the numerator, I'm just going to put it up with the 1 times radical 3. So the best formula, radical 3 over 4, s squared. What I'm going to do with that, so let me go back here and write them. So that was area, area of an equilateral triangle. Radical 3 over 4 s squared. It wants the rate of change of the area. So now we do the derivative, and that'll be the rate of change formula. Again, this is a number, so I bring down the 2 here. I can reduce the 2 over 4 to 1/2. And then I subtract 1 from the 2 in the s squared. So this becomes s to the first. So again, here what it is, 2 over 4 cancels out to be 1/2. I just didn't write the 1 and just left the radical 3 over 2. Okay. That's it. And now the next question, we just plug in certain values. So to finish this one, I'm not going to do C again. It wants the rate of change at 2 and 10. So I plug in 2 into the derivative, which is this. So it's radical 3 over 2 times 2. That'll cancel out, just be radical 3. And then I plug in 10, radical 3 over 2 times 10. 10 over 2, this will end up being 5, and then radical 3. This one's a little more directly proportional. 2 times 5 is 10 here, it's just 5 times as much. Alright, so again, start with the formula. You'll make sure it's in terms of one variable. Might just have it, might have to do a little work. Do the derivative and then plug in the value. You get the rate of change of it. Sounds good. I want to talk about position, velocity, acceleration next. Any thoughts on the shape ones though? Okay. So let me talk about the relationship between position, velocity, and acceleration. Again, if you are or were in physics, this is like going to sound pretty familiar. First thing is, position is often s. We say s of t. It's a function based on time. So the variable here will be, you can call it anything. We usually say t is the time. Sometimes it'll be h for height, but often it's s for position. Why do we not use p? Not sure. Maybe p is perimeter. So in calc, we don't always use s for position. V will be velocity, and a will be acceleration. So position, it just gives you where you're at, right? I mean, it just gives you sometimes it's on a coordinate axis, sometimes on a grid, it tells you where you're at in relation to time. Before I talk about velocity, let me talk about displacement. Thanks. Yeah, you can just set it up there. Do you guys know the concept of displacement? The difference from start to end. So here's just a quick example. If I walk forward 3 steps and then step backwards 1 step, my total distance was 4, but my displacement was only 2. Right? Start to stop. Where do you end up? So a simple way that we can do that if we have a position function is s of b minus s of a. If I write it like this, does it look familiar? S of b minus s of a over b minus a? What was this formula? A-rock. Yeah, this was average rate of change. So displacement, we've actually already done. It's just you don't have to divide by the denominator. It's just the numerator of average rate of change. So thank you. So let me get rid of it. And yes, we say s now instead of f. But it is just the numerator, so I don't think I have it on here. Numerator output of a-rock. You can also think of it, yes, as just start to stop. So where do you stop? That's what we do this one first, the b minus where you start, and that will give you displacement. Just the numerator of average rate of change. Okay, next one is velocity and speed. So here's the great thing. You do the derivative of position, a function that models the position, and you get the velocity. Derivative of position is velocity. What do I say here? The instantaneous velocity. So what it represents is the rate of change of your position. How fast rate of change? How fast rate of change of the position function. So really I got this. Position function. If you do a derivative, you will get the velocity function. I'm jumping ahead here, but then you do the derivative of velocity, and guess what? You get the acceleration function. That's how these three are related. So original function, first derivative is velocity, second derivative is acceleration. I skipped ahead here. What did I want to say? Speed, if you've heard that, versus velocity. Speed can be, can only be positive. Velocity can be negative. So that's the only difference we say there. Like, oh, you get negative 20 for the velocity. Well, the speed of it is actually just a positive 20. But velocity can't be negative. Well, there we go. Let's say, and then I'm down here with acceleration. I already said it's the rate of change. Acceleration represents rate of change of velocity. How fast is velocity changing? Oh. It is the derivative of the velocity, which is the second derivative of position. So I will review this from time to time, but here's how it goes. SVA. You do a derivative of this one, you get velocity. You do a derivative of this one, you get acceleration. That's what we got. Okay, let's just try. Probably I'm just gonna do the first example on the next page. That's pretty much all I'm gonna do. Any thoughts on these? Let me ask this: if you're in physics, do you do derivatives at all? So like, did you know that it was a derivative here to get the velocity?
He told us that it was derivatives, but we haven't done it that way.
You haven't done it, yeah. Okay.
You do it differently. Try to find displacement stuff. Like have an equation.
Yeah, I was gonna say there might be. They're all related, of course, but it's probably just some slight variations. Or maybe-
Distance talk instead of
Yeah,
calc talk.
yeah. It might also be you would give basically he might give you different things.
Yeah, you're given like this and this.
Yeah, based on you might have different things provided, so then you have to do something else to find it. All right, sounds good. Let's look at the next one. So on the next page, an object moves along a coordinate line, so its position s in meters satisfies this function. Because for now, they basically have to give you a starting function for these. That models this object. So what I want to tell you about this, actually, I want to ask you this in physics too, if you did this. Basically, what's happening? You have usually it's a point. They say an object or a point. It's moving back along a line. It might go backwards this way, or it might go forwards. We can't really see it visually, so what we do, at least in calculus, is we do this. Wherever it starts, maybe it starts here. We draw a curve. So maybe it goes this way, then we curve it around this way. And then we might curve it back this
We
way.
don't do curves.
So that's how you'll see it visually in here. Yep.
Like in physics, you do dot like slashes for each second, for how long it counts for each second. And then you do dots for like where it stays still. And then
Oh,
go backwards.
that's true. Like here, that's like something here we're gonna find. Oh, right here,
Stayed still for 2 seconds.
it moved to the it's like I'm moving this direction, but then I stopped and I changed directions and I moved backwards and then here I changed direction
Yeah.
again. So in calc, we visually have to see it. I curve it around. That's how we see it. It's really just moving back and forth along a line. All right, here we go. So find the displacement and average velocity during the first 3 seconds. Now, before I even write down those formulas, first 3 seconds. Lots of times students say, all right, where are we starting? We're ending at 3 seconds, right? That's the end. But we started at 0 seconds. Yeah. Lots of times students will go, let's say we're going from 1 to 3. And I'm like, well, we still got it, what about 0.5 seconds and 0.6 seconds? So the question didn't state it exactly, but it's in there. The first 3 seconds, that's from 0 to 3 seconds. So displacement, start with you. I'm just going to write down all average rate of change, in this case, average velocity. Average velocity is just the normal formula. I just change the s instead. So if I just did the numerator, that's displacement. My a is 0 and my b is 3. So let me start with just that one. S of 3 minus S of 0. Oh, I don't need that one. S of 3 minus S of 0. I'd like to not take a lot of class time to work this out, but you plug in 3 right here and here. You work it out. You get negative 10. Minus, you plug in 0. I can do that one. 0, 0, you get 8. So that is the displacement. Oh, by the way, 0, this is where we start, right? S of 0. At 0, you start at negative 8. So here, I'll make a little drawing of what's going on. Here's 0. Here's negative, here's negative 8. You start here. And here's all we know, I guess. At 0, we're at negative 8, and at 3 seconds, we're at negative 10. So I guess I don't actually know. It could have gone right first and then back left, or it could have just gone directly here to negative 10. Well, the displacement is negative 18. Oh, it's 8. What am I? I'm sorry. I was like, why is this not working? It's 8. This is just part of the formula, the minus. So we started when time is 0, it would be 8. That's the position. Okay, and then we went negative 18. So it goes this way. Sorry about that. So that's what's going on. It's going to turn here in a second. That's displacement. So I'll change colors. Average velocity then is when you complete the formula. So you put this over, so really I could have gone back here, over b minus a. So over 3 minus 0, which is 3. Which you get negative 6 meters per second. I just realized I forgot to write meters here. It did give us units. Okay, so displacement, average velocity go together. If you have average velocity, you really actually already did displacement. It's the numerator. Let's, I'm just going to finish up the last ones on here. Thoughts on A? Or over that one? Find the velocity. That implies instantaneous rate of change. If I want an average, I'd say. So this implies instantaneous, which is a derivative. So this wants the v of t, which is the velocity function. It's the derivative. Derivative of position. So it is 4t minus 12. So part A was average velocity. That was, okay, what's the average rate of change between 0 and 3 seconds? This is, what is the exact rate of change at 3 seconds? Right, it's a tangent line. It's a tangent line. So whatever's going on right here. Exact rate of change at 3 seconds. So we plug in, we want v of 3. So we're going to plug in 3 there. 4 times 3 minus 12. And we get 12 minus 12, which is 0. So there's a clue. At 3 seconds, it has stopped, or at least like it could be just instantaneously stopped, change direction. Or perhaps it stops and it's going to stay there. But changing direction, or it could just, I could stop and then I could keep going. Probably going to change direction. So let's answer part C. When does the object change directions? Kind of didn't mean to put it all there. Well, when it reaches a rate of change of 0. So I'm going to put that was at 3 seconds. Guys, later in the year, I'll be able to show you how we can verify that we knew it didn't just stop. So it just stopped and then kept going in the same direction. But we actually would know this when it would change direction. I'll be able to show you why I know that for sure later in the year. Okay, last two here. What is the position of the object? So sometimes, you know, as you walk through these, really just focus on a couple words that tell you what to do. What is the position? This is back to x, the original function. What is the position of the object when it changes direction? Well, we just found it changed direction at 3 seconds. That's when it changed direction. That was from part C. They want the position. So we need the position at 3 seconds. S of 3. We already did it. It was right here. S of 3, already did it. Negative 10 meters. Kind of already graphed it here too. By the way, what it's going to have is going to change direction, starting to go this way. Sounds good. Okay, and last one, I'll see if there's any questions. When is the acceleration positive? We haven't even done the acceleration yet. So let's find it. The acceleration is the derivative of velocity. Or the second derivative of position. So here's velocity, first derivative. Second derivative here is 4. So how would you answer this? When is the acceleration positive? Hmm? Well, this is the acceleration it's forward. Any other thoughts? When is the acceleration positive?
Always.
There we go. Always. Yeah. So if you had gotten something with like t in here, then we would have had to find when that expression was greater than 0. What we found is the acceleration is it's always positive. The acceleration, yeah, is actually always positive. So if we got -2, you would have said never. Because the acceleration was always -2. But basically this means velocity is always increasing.